Good morning, all of you. We shall now discuss about the topics of Unit 4. In Unit 4, we have economics of machining, design of shanks for single point cutting tools, broaching tools, and design of milling cutters. We shall discuss each topic one by one. First, we shall discuss about the economics of machining. Economics of machining. In any manufacturing operation, we should understand that the cost of the operation plays a vital role in determining the speed of the operation. In metal cutting also it is true. If we cut excess or unwanted material at slow speed, time of completion of the operation increases, and therefore the machine operation, cost of labor, machine operation, overheads are going to increase, making the machining process costly. If the same machining is done too fast, wear of the cutting tools is excessive. So the machinist has to frequently change the cutting tool, regrind it, reset on the machine, and then start machining again. Uh, so we have to understand that I can cut at condition 1 low speed or condition 2 high speed. So each of them have advantages as well as limitations. Therefore, we have to strike a optimum condition. We have to strike a optimum condition at what cutting speed a cutting may be performed. Here one has to understand that not only this cutting speed, we have many more parameters like feed, depth of cut, lubricant usage, type of the cutting tool material, and so many other parameters which can be optimized. But most of the times, speed, feed, and depth of cut (VFT). These are the simple conditions which can be controlled so that we can obtain the optimum values leading to minimum cost or maximum production rate. Now let us look to how optimum cutting conditions can be arrived at. So arriving at the optimum cutting conditions. In these discussions, though we find VFT depth, likewise lubricant usage, cutting tool material, etc., we have them different possibilities. We are going to consider this cutting speed as the most important parameter, and we shall try to work out how this V can be optimized so that we get the we are going to reach the economics, or we can or the cutting can be economical, right? Here when I mean by economical, we should understand what is the meaning of economical. So once I mean by economical, I also mean optimum. So I am going to achieve the optimum cutting speed with different points in mind. I can either minimize the cutting cost, or I can maximize the production rate. We shall discuss about these two optimum criterion in detail. So this is called as criterion 1, and most popularly this is called as Gilbert model. So this is called as Gilbert's model 1, where we consider to minimize the cutting cost. Model 2, we try to maximize the production rate. Both of them need not give the same cutting speed. Let us first discuss about what are the costs that are involved in turning operation. First one, labor cost. So labor cost, which may include the salaries or rather wages of the workers who are directly involved. Machine operating cost. This includes interest on the cost of the machine, depreciation, power consumed in operation, machine maintenance cost, overheads, cost of establishments like buildings, land, office, salaries for the staff who are involved in the office, etc. Next, job handling cost, cost pertaining to loading and unloading the jobs, machine idle time, etc. Next, cost of tool material. Tools are consumed away because they will get wear away on usage. Hence, they also have to be accounted for. Next, cost of the resetting tool. So, resetting involves regrinding the tool or bringing a new tool into position and fitting it again so that the production can continue. Let us look to the uh, costs that may be involved in a simple turning operation. So, let us take the case of simple turning. That means I will turn a job, say over length L. So, this is the length L of diameter D. I will do the turning operation, simple turning operation, and reduce the diameter to small d, say. So, the diameter here is small d. So, in carrying out this operation, let us see how the cost can be calculated. First one, cost of cutting action. That is the first cost. What is the expression for this cutting action cost? So, I write it as Cu into Tm. What is this Cu? Cu is nothing but the machine operating cost, which includes labor rate. That means how much the person is going to be paid. Generally, we take this per minute because the calculation per minute is more appropriate. Though we may pay the operator per hour or per day or per shift, here the calculations will be convenient if we take it per minute. So all the times which I consider, they will be per minute. Next, what is this TM? TM is nothing but the measuring time per job. I can write it as L by F into N. Um, this F can be obtained by considering the expression for cutting velocity V. So V I write it as pi dn by 1000, T is the diameter in mm, and N is the RPM. So which gives N is equal to 1000 V by pi d. And accordingly I may write this measuring time Tm as pi dl by 1000 Vf. Right? So this I need to substitute. Therefore I have put it in a box. Next type of cost, that is job handling cost. So job handling cost refers to the time for loading and unloading one job and its corresponding labor rate, Cu into Th. So both of the things are multiplied. Next, cutting cost, cutting tool material cost. So here it is material cost. This rather tool material cost. So how much or how do I allocate that? So I write it as Ce into Tm by T. Tm by T refers to the number of times I am going to replace the cutting tool or rather do the regrinding for the cutting tool in a given machining time Tm. So therefore T refers to the tool life. So I can write Ce in two ways. If they are the ceramics or cardboard tips, that means throwaway tips, I may write it as Ce as cost of the tool bit by number of cutting edges per bit. On the other hand, if it is HSS tools or high carbon steels or stellites, that means regrindable tools. So they are regrindable tools. I can write this as cost of the tool divided by number of times the tool can be reground, including the regrinding cost. Next, tool setting cost. So tool setting cost is equal to Cu into Tm by T into Ts. So number of times I replace the tool and Ts for the tool setting time per job, and Cu refers to the labor rate. So total cost, I have to add up all this cost, Cu into Tm, Cu Ts, Ce, Tm by T, Cu into Tm by T into Ts. Now the aim is to find the cutting velocity which gives which gives me, now the aim is to find cutting velocity which gives me total, minimum total machining cost. So I differentiate this total cost CP with respect to V, and the differentiation is partial differentiation, and of course further substitute it, equate it to 0. So making a substitution of all these terms, Tm is equal to pi dl by 1000 Vf, as well as Vt power n is equal to constant. That means this is coming from Taylor's tool life equation. Taylor's tool life. This is coming from Taylor's tool life equation. Okay. So I write it as pi d L by 1000 Vf, and T is equal to C by V to the power of 1 by n. So if I make the substitutions, I get finally the optimum cutting velocity for minimum measuring cost as C divided by 1 by n minus 1 Ts plus Ce by Cu full brackets to the power of n. If I understand this as T, so this is going to be the optimum tool life. T opt is equal to 1 by n minus 1 Ts plus Cu by Ce by Cu, right? So if we look to all this cost put into a simple diagram, how it looks like, see. So the handling cost, which is a fixed cost, machining cost, it goes on decreasing continuously. Tool material cost goes on increasing rapidly when I increase the cutting speed. Tool changing cost, this cost is going to also increase in line with the tool material cost, or number of times I need to change the cutting tool or regrind the cutting tool. Adding up all the costs, we have a U-shaped curve. So we find this is going to be the optimum cutting velocity V opt, and likewise this is the minimum unit cost per piece, and of course this includes only the cutting cost. It does not include the tool material cost. It does not include the work material cost. So you can work out a problem based on these grounds. So Vt power 0.5650 cutting velocity. So, so a batch of 1000 steel parts is to be produced, 100 mm diameter, 250 mm length. Feed is fixed up 0.2 mm per revolution. Cost per 850. Time to reset 1 minute Ts. And the machine rate 300 per hour. So we are required to find optimum cutting cost, which gives minimum, optimum cutting speed, which gives me the minimum cost, corresponding tool life, production rate, right? Time to load and unload is 2 minutes. So this I can write it as Ts, and of course I have to include this 2 hours also when I take up the total production time. So this 300 per hour has to be converted into rupees per minute. So feed F, diameter D, cost per cutting edge. So this is CE. Time to reset the tool. So this is TS. Sorry, this is going to be TH. It's not TS. It is TH. Okay. So if we carry out the exercise, we get optimum velocity C by 1 minus 1 by n minus 1 Ts plus Ce by Cu to the power of n. So 271 meters per minute. So using Vt power n is equal to C, I can obtain the optimum tool life to be 33 minutes. So total production cost, if I consider for 1000 pieces, so 1000, so time of the initial setup, I should consider time of the initial setup also, plus 1000 cu into tm cu th ce. So all this are included, and measuring time, if you make a calculation, pi dl by 1000 vf opt, it is come to be 1.45 minutes. That means 1 point every 1.45 minutes I am likely to get a component, and the total cost is 20,267, and total production time. So time for initial setup, that is 2 hours converted into minutes, it is 120 minutes. Measuring time is included, handling time is included, setting time into number of sittings, right? So this will give a value of 3614 minutes, right? So this is the discussion regarding the way how we can obtain the cutting velocity, which gives the minimum cost in turning operation. So this is called as Gilbert's model 1. Gilbert's model 1. Likewise, we have Gilbert's model 2 also. So this model 2, it is telling about how we can obtain the cutting velocity for maximum production rate. So this is Gilbert's model 2. So production rate, since sometimes cost may not be the only criterion. We have to consider production rate. We may be in a hurry to produce components, large number of components in a short period of time. In such situations, slight increase in cost does not matter, and therefore we try to bother about the production rate, which we call it as maximum production rate. So in this context, we have to consider what is the time required to produce one workpiece. TP, time required to produce one workpiece, is equal to TM, measuring time, TM by T into TS, tool setting time, measuring time by tool life, plus TL, loading and unloading times. Production rate, I write it RP, is nothing but the reciprocal of this TP. So for maximum production rate, I may write dou RP by dou V is equal to 0. So dou by dou V of 1 by TP is equal to 0, right? So it will also lead to dou TT by dou V. So if I try to make substitutions of the expressions for Tm as well as T, and I try to differentiate, I get an optimum cutting velocity as C divided by 1 by n minus 1 into Ts to the power of whole to the power of n, and corresponding tool life 1 by n minus 1 into Ts. So if you look to the graphical observation, how the different times are likely to change, you may find that the total time for producing one component with a particular cutting speed also takes a U shape. In this, similar to the previous case, we are getting the measuring time reducing as cutting speed increases. However, the tool changing time is also going to increase, and we don't find another line as in previous case. So that is a term which is connected about the tool cost. We don't bother about the tool cost, right? So this is regarding the economics of machining. So we should also keep in mind. So keep in mind that optimum conditions, that means optimum cutting speed, cannot always be used. So what are the reasons for that? One, the drives available are step drives. Second, machine tool may not be rigid, may not be rigid enough. Right. So this is about economics of measuring. So next we shall discuss about the multi-point cutting tools as well as shank design for a single point cutting tool. First we shall discuss about the broaching tools. So broaching is a process where we enlarge the holes which are already available are made by drilling process or punching process or casting process, whatever be the process. It's only an enlargement process. It is not going to start any hole. Further, we may understand that this is going to be a production process which produces components to very high degree of accuracy. The accuracy is going to be very good and excellent surface finish. And one need to understand that both roughing and finishing are completed in one stroke or rather one pass of the cutting tool. So limitations are also there. Broaching machine is expensive, very specialized. Broaching cannot be used to machine blind holes. There should not be any obstruction in path of movement of the cutting tool. Amount of stock that can be removed is also limited, 6 mm or lesser. Uh, Next, let us look to the tool, which we call it as broach. So broach is nothing but a bar-shaped special cutting tool provided with a series of regularly spaced teeth. Each, each tooth has a different height. The height is going to be progressively increasing. That is how the cutting gradually increases the dimension of the hole. So the cutting is going to be progressive. That's why height of the teeth are also progressively increasing. Further, the broach may be a pull broach or a push broach. Roughing operations, finishing operations, both of them are completed by single stroke of this tool, which we call it as broach. So this is a push broach. So by applying a push force to this push end, once the front pilot ends, gradually the whole of the workpiece. So this is the whole of the workpiece. It can be enlarged by pushing this broach. So you may find tooth dimensions are also gradually increasing in this order. So another type of broach, it is pull broach. So the broach which we find here is called as push broach. So the next broach which we find here, it is called as pull broach. So this is a pull broach. Pull broaches are more popular than push broaches because there is less scope of buckling of this broach. If we look to the parts of this tool, you may find multiple number of parts. So the pulley end, neck, front pilot, roughing teeth, that means the teeth which perform the roughing operation, semi-finishing teeth, the teeth which perform partly finishing and partly roughing, and finally finishing teeth. So there is a rear pilot and follow rest. So we find a neck here and a pulley end. So the machine holds this neck and pulls the tool, right? So we may find a sort of reduction in dimensions of the neck. So this is how the tooth may look like. So the pitch of the tooth slightly inclined downwards. So clearance, cutting surface inclined slightly backwards to make it sharp, which we call it as rake angle. And this space is called as a gullet space. And the H is nothing but the depth of this gullet space. Okay, let us look to what are the considerations that are observed in design of this broach tool. First, we have to design what should be the length of the broach. So length of the broach is equal to total length of broach is equal to length of cutting portion, length of finishing portion, length of pulley and neck, front and rear pilot. Length of cutting portion, we write it as PC into ZC. Z stands for the number of tooth. P stands for the pitch. So length of finishing portion, length of cutting portion, that have to be decided. When we talk about this length, length of front pilot, first length of front pilot, how much it shall be? It shall be taken generally equal to the length of the hole that has to be broached. That should be the length of the front pilot, and its diameter should be equal to the minimum diameter of the previously machined hole, that means starting hole. Next, diameter of the first cutting tooth, that is also important. Diameter of the first cutting tooth should also be equal to the diameter of the front pilot. Next, overall shank length is made sufficiently enough to see that the tool, while passing through the fixture and the job, the pulley and neck shall be properly gripped. Right? The diameter of the neck, as we have observed, is made slightly smaller so that the grip is going to be firm. Let us talk about the number of teeth. So when we talk about this number of teeth, so T by TA plus TS. T is equal to depth of cut, total depth of cut. That means we want to enlarge a hole from 20 diameter to 46 diameter. This total depth of cut is equal to 46 minus 20 by 2, that is equal to 13 mm. Next, TA stands for the average depth of cut per tooth. Generally, it is taken as 0.02 to 0.12 mm. It all depends upon the material, type of loading desired, etc. Next, S is equal to number of safety teeth. The number of finishing teeth, it will vary from 4 to 8. The purpose of providing so many finishing teeth, it is that during the life of the broach, it is reground several times, and the reserve of the finishing teeth provides a last cutting teeth of same size as the desired dimension. That means when we go on use the broach, we find that it will wear out. On account of its wearing out, we should see that we regrind it. When we regrind it, the finishing teeth also dimensions can change. So better we reduce the dimension of finishing teeth by small amount. I mean, the will reduce the size of the finishing teeth towards the roughing end, and then gradually increase towards the finishing teeth. That will provide more life for the cutting tool. Next, pitch. Pitch of the teeth is taken as 1.25 to 1.5 times of root L. So this is an empirical formula. So the formula has been arrived at based on observations or rather experience. And here L should be understood as length of the hole to be broached. Next, height of the tooth. The cutting action and chip formation in the gullet space you can find here. So this is the space that is available for the chip. And if the chip starts coiling inside this gullet space, it can take this shape in this manner. The effect area of this gullet space is AE is equal to pi by 4 h square. I write it as pi by 4 h square. We equate this to the chip dimensions. I write it as K2 into TA into L. TA stands for the depth of cut, right, per tooth, right? TA into L, K2. So TA into L will stand for the cross section area, or rather the length of the chip that is covered in one pitch. So small, this is small L. It's not capital L. This is small l. So it may be understood as length of chip handled by one tooth. So it can be understood as even as pitch of tooth. So h is equal to 4 by pi TALK2, right? So this is the height of the bullet space. Next, width of the tooth. So width of the tooth is to be sufficient enough to give strength to the cutting edges. W is this generally taken as 0.3 to 0.4 times of the pitch. Rake angle. See, rake angle is taken depending upon the material and work material and tool metal combinations. Further, it is going to be taken depending upon the nature of the teeth, whether it's roughing teeth or finishing teeth. For example, for roughing teeth, I can have 10 to 20 degrees of rake angle. Finishing teeth, it can be only 5 degrees. Next, relief angle. Relief angle is provided so that there is not going to be unnecessary rubbing of the teeth with the work material. So generally provided 2 to 4 degrees. Next, radius of the gullet space. It is 0.2 to 0.35 times of P. Broach tools are generally made up of 1841 HSS by grinding process after hardening, proper hardening. Sometimes carbide broaches are also used, right? So carbide broaches, they are used to broach cast iron particularly, right? So this is regarding the broaching tools. Continuing the discussion, we shall discuss now about the shank design for single point cutting tools. In the first chapter, we discussed about the tool point, so the main cutting portion where we find the different geometrical elements like rake surface, flanks, the cutting edges, tool nose, each of them ground in a particular manner so that we obtain the enough sharpness for the cutting tool. We have to look to the other end of the cutting tool. The other end of the cutting tool is nothing but the tool shank. This tool shank supports the tool point. So tool shank supports tool point, and therefore we should see that the tool shank should be sufficiently strong so that it does not itself break away without giving any support. The shank, it can be of square cross section, rectangular cross section, or circular cross section. Rectangular section is often preferred because we find it strong, right? Rectangular section is commonly used since reduction in its strength is less compared to other sections. And of course, this happens when a seat is cut for an insert. If we try to cut some portion so that we add up an insert, then we have enough strength there. So for all such reasons, we can have the shanks of rectangular cross section. See, in rectangular cross section also, we may understand that the depth or height of the tool is going to be more compared to the width. So this type of rectangular section is preferred rather than rectangular section of this shape. So this is not preferred and this is preferred, right? So when we talk about the design issues for this tool shank, we have to design it based on two important issues. One, it is strength point, another it is rigidity point. So let us first look to how it can be designed for strength. Strength here means bending strength. Supposing this is the length L, right? It is similar to the length that has been supported beyond the fixed end of the cantilever. So this tool is treated as a cantilever. So tool treated as cantilever. So we find the cutting force Fc in this place. Fc is the cutting force. Fc is the cutting force, and L is nothing but the overhang of the tip of the tool. Now moment, we may observe that M is equal to moment about the fixed end. Moment about the fixed end. Say MO about this place, point O. It is going to be Fc into L, and this moment of resistance. This is going to be the bending moment. And when we talk about the bending properties, we may write moment of resistance Mr. So Mr is equal to BH cube by 6 into sigma h. So this we are getting from bending equation, from bending equation. So the bending equation says M by I is equal to E by R is equal to sigma by Y. So the sigma by Y, M by I are simply M from this equation is equal to I into sigma by Y. So this gives B square by 6. B stands for the width and H stands for the height. So if it is a circular cross section where we refer in case of boring tools, we get it pi d cube by 32. Normally the value of H by B are preferred as 1.25 in case of roughing operations and 1.6 in case of semi-finishing and finishing operations. Length of the overhang is generally kept low. It is generally 1 to 1.5 times of height H. So we are going to decide what is going to be the value of H, B, L. So L is nothing but the overhang. So with the help of these relations, the dimensions of the tool shank, when I look at it is B and H, and of course L. When I talk about L, it is generally kept as a value of H. So what I need to obtain is nothing but H and B. So if I have an allowable value of sigma B, that means bending stress which is allowable, I can calculate the value of H and B, right? By calculating what is going to be the cutting force Fc. Cutting force Fc may be given, and using that L is equal to 1.25 or 1.5, 1 to 1.5 times of H, right? I can make a substitution and obtain M. So when I have this M numerical value, I put it to the left hand side, and I have B and H. Sigma B is known. Relationship between B and H is also fixed up depending upon whether it is a roughing operation or a finishing operation. So in that way, it is possible for me to find out the value of H as well as B, right? So once this calculation is made, I should also check the design whether it is safe from deflection point of view or rigidity point of view. So I had told you in the beginning. So when I design the tool, I design from strength point of view, and also from rigidity point of view. So we have seen that how we have designed from rigid strength point of view by considering the bending strength. Now we can see how we can verify whether it's rigid or not. So rigidity here means deflection. So how much is going to the deflection? See, we are required to limit the amount of deflection to zero point 0.1 mm for rough turning and 0.05 mm for finishing operation. This is done so that that deflection is not excessive and we are going to get the required finish. Likewise, the tool shall not be subjected to a sort of chatter. So delta can be found by WL cube by so this is the deflection equation for cantilever WL cube by BH cube by 6. Okay. Hmm. So this is the cantilever deflection equation. So we will verify whether this deflection obtained is within the limits of this 0.0, 0.1 or 0.05 depending upon whether the operation is a finishing operation or roughing operation, right? So this completes the discussion on design of shanks for single point cutting tools, shank design. Okay, next we shall talk about the design of milling cutters. So milling cutters, the design is an exhaustive process. However, I will outline you what are the important features that may be covered so that the milling cutter design is almost complete. So milling cutters, if we look to the milling cutters, so these are nothing but the multi-point cutting tools. So they have number of cutting teeth spaced around the periphery. So milling cutters may be classified as profile relieved milling cutters and form relieved milling cutters. So milling cutters, they are sharpened uh, by having a land. So you can look to the milling processes. So milling may be peripheral milling or face milling. And when we look to the nomenclature of a single or a rather simple milling cutter, so body, arbor, the central supporting portion, shank, cutting edge, land, flutes, face, fillet, helix angle, diameter, relief angle, primary relief, secondary relief, radial rake, right? So you can find all these features here. So tooth, multiple of tooth are there. This is a plain milling cutter. So radial rake angle. So you may find the tooth inclined backwards. So some portion it is straight. I mean inclined by small quantity. Later portion it is inclined by large quantity. Primary relief, secondary relief. Rake surface and the cutting edge and some straight portion which we call it as land. So let us look to the different features. First one we call it as the size of the cutter. Size stands for the outermost diameter. So when I talk about this outermost diameter, so it is nothing but equal to arbor diameter, thickness of the cutter ring, and height of the tooth, of course, again twice. So larger cutter diameter will give more flute depth. It will result in better heat removal, longer tool life, and higher cutting rates. But when I talk about the large cutting diameter, I require more torque. So it requires more torque and it is likely to even have more of deflection. So more of cutting tool metal is there required in this case again and more measuring and a higher tool cost finally. So smaller cutter means lesser torque and it will deflect less, but it will be cheaper. So I have to strike a break even. Generally, the cutting diameter by practice, it is taken about 2 to 3 times of the arbor diameter. So that is a practice, it is felt sufficient. So the cutter hub diameter, so cutter hub, so immediately after the hole for the arbor, so some portion is thickened, so that is equal to diameter d plus 2 times of the thickness of the body. So that is the cutter hub diameter. Next, tool angles. So we are having different tool angles. Helix angle. So for plain milling cutters as well as side and end milling cutters, we have different helix angles. Next, radial rake, 10 to 20 degrees for cutting materials, cutting softer materials, and for harder materials, we have smaller rake angles. Of course, carbide tool cutters, when we use them, we have 10 to 15 degrees. Relief angles. So the relief angles are provided to eliminate the heel drag. That means the heels are not expected to rub against the workpiece. So this will reduce the friction, and it will also help in heat dissipation. Width of the land, 0.127 to 254, 3.2 for large dia cutters. And the number of teeth, this is an important point. How much should be the number of teeth? It is always a question. So n, we write it as f by f into n, ft into n. F stands for the feed rate, mm per minute. Ft, feed rate per tooth, feed per tooth. Feed per tooth is a practice which is followed for milling cutters. So n is a cutter speed in RPM. For plain milling cutters, generally 0.05 to 0.6 mm per tooth is often taken. And for, of course, depending upon the type of materials, we do more feed. If it's a relatively soft material or convenient material, we take it as high as even 0.8 mm per tooth. So using this, we can be able to calculate the number of teeth. Next, material removal rate, MRR. So this material removal rate, W into H into F, if we calculate width of cut, depth of cut, and of course feed. So, and further, we have to prevent the overloading of the machine motor. We have to consider all the different variables in a single place. I have to write N as number of tooth is equal to K into HPC, horsepower available at the cutter, divided by F into N into H into W. So K is a machinability factor. So depending upon the material, we have to consider the value of K. So aluminium, magnesium, such type of soft materials, they are very good machinable. Therefore, we can consider more the value of K. If we go down, so for example, I take monal metal, it is only 9, right? So it all depends upon the work material. Next, cutter diameter, the number of tooth in this cutter teeth may be taken as C into root of D. This is also one way. So for solid cutters, 2 to 2.8 shall be the value of C, and 0.6 into 1.05 is a case for fine tooth. So coarse tooth, fine tooth. Depending upon that, I can take the value of C and decide upon the value of number of cutter tooth. Power requirements. Once again, HP, it is the value of horsepower required the cutter. I write it as metal removal rate centimeter cube per minute by K. So we might find this terms already have come in this MRR as well as N. So a combined consideration of these parameters shall give the values of the value of number of teeth, feed that may be selected, what shall be the width of the cutter, and what shall be the depth of the space. Right? So this will complete the discussion on the multi-point cutting tools also. Thank you.